Imagine a computer so powerful it could solve complex problems in a fraction of the time it takes today's supercomputers. In this episode, we will explore quantum computing, including its potential applications, advantages, and challenges, as well as the direction this revolutionary technology may be heading to. Get ready for a quantum leap into the future. Before we continue, make sure to subscribe for more on emerging trends in information and communications technology. In classical computing and digital communications, binary digit, or bit, is the basic unit of information. Classical computers operate using bits, 1 and 0, which represent DC voltage levels, for example, +1 volt and -1 volt. Thus, bit is physically perceived as a two-state device. Quantum computing is based on the quantum behavior of a variety of basic particles such as electrons and photons. For example, charging or separation of ions can successfully be exploited to serve as a symbol 0 and/or 1. A quantum bit, or qubit, is used as the basic unit of quantum information in quantum computing. The values assumed by a qubit may be represented by points on the surface of sphere of unit radius. The qubit reduces to bit 1 at the south pole of the sphere and to bit 0 at the north pole. In that sense, bits 1 and 0 are special cases of a qubit. As opposed to classical bits, which are either in a state of 0 or 1 with 100% probability, qubits can exist in a coherent superposition of states, which means they can represent either 0, 1, or superposition of both at the same time. The measurement of a qubit would destroy its coherence and irreversibly damage the superposition state, although a measurement of a classical bit would not. Consequently, the measurement of a qubit leads to one of the two possible outcomes, namely bits 0 or 1. Special properties of qubits, such as the principles of superposition and entanglement, contribute to the extraordinary capabilities of quantum computers. In quantum mechanics, superposition refers to the ability for a quantum system to be in multiple states at the same time until it is measured. The computational power of classical computing increases linearly with the number of bits. This means that, in classical computing, doubling the number of bits will only double the computational space. Whereas computational power increases exponentially in quantum computing with the addition of one more qubit. Hence, quantum computing can be used to solve complex problems using only a limited number of qubits. Due to their enhanced computational capabilities, quantum computers are capable of processing enormous amounts of information simultaneously. However, the loading of large data sets into quantum states is still an open question. Another important concept in quantum mechanics is quantum entanglement. Quantum particles, such as a pair of photons or electrons, form correlations with each other. Hence, the quantum state of one particle could be determined from the state of the other particle, regardless of the distance between them, when the state was measured. Thus, a change induced in one will affect the other. Contrary to bits, which can be set independently, qubits can be placed in entangled states, in which a change in one qubit will instantly affect the other qubits irrespective of their location. Increasing the number of qubits entangled together increases the system's ability to perform calculations exponentially. Due to its highly susceptible nature to interference, entanglement also presents a weakness in quantum computing. In the absence of entanglement, quantum computing loses its advantage. Another important concept in quantum mechanics is the uncertainty principle, which highlights the fundamental difference between the quantum mechanics and the classical mechanics. In contrast with classical mechanics, quantum mechanics states that physical properties cannot be measured with arbitrary precision. The higher the certainty with which we know one of the physical properties, the lower the certainty with which we can know the other. For example, the more accurately one knows a particle's position, the less accurate one can know its momentum, and vice versa. Quantum computers manipulate qubits using quantum gates, just as classical computers use logic gates. Quantum computers can perform various algorithms and calculations by applying a sequence of quantum gates. Quantum algorithms take advantage of quantum computing's unique properties, including superposition and entanglement, which is possible due to the uncertainty principle. There are a number of well-known quantum algorithms, including Shor's algorithm for integer factorization, Grover's algorithm for unstructured search, and quantum phase estimation. Compared to classical algorithms, these algorithms are capable of solving problems exponentially faster, making them ideally suited for tasks such as cryptography, optimization, and quantum simulations. Since the state of quantum particles cannot be precisely determined, probabilistic nature of quantum states represents multiple possibilities at the same time. When qubits are manipulated using quantum gates, their states are changed according to the uncertainty principle. Error correction and maintaining coherence in quantum computing are particularly challenging due to the inherent uncertainty in qubit states. To address these issues, researchers are developing fault-tolerant quantum computing techniques and error-correcting codes. Also, this principle underscores the difficulties associated with developing practical quantum computing systems, since it contributes to error correction, and to overcome the difficulty of maintaining coherence. In theory, a qubit can encode one bit completely, but it can also hold more information, for example, 2 bits when dense coding is employed. Using superdense coding, a transmitter and receiver can communicate using only a small number of bits, as opposed to many bits, provided they have previously shared an entangled resource. Eavesdroppers cannot intercept messages since both qubits are required for decoding information. When an observer measures a quantum system, the system is forced to collapse into a definite state, and to change in response to the observation. Once a qubit is measured, its superposition is lost, as well as its entanglement with other qubits. Quantum simulations can, however, be observed without disrupting them using a technique known as quantum measurement without collapse. A quantum measurement without collapse allows the observer to measure the system without disturbing its quantum state, thereby avoiding its collapse. There have already been a number of experiments that have demonstrated this. For example, the spin of a single electron was measured without causing it to collapse. Similarly, the position of a single atom has been measured without causing it to collapse. The development of quantum measurement without collapse may have many applications in quantum technology. Among these are the development of new quantum computers that are more efficient than current computers, and the development of new quantum sensors that are more sensitive than current sensors. However, decoherence is a major obstacle to the development of large-scale, practical quantum computers. Research efforts are underway to develop error-correcting codes and fault-tolerant quantum computing techniques to overcome this issue. Applications. Quantum computing offers several groundbreaking applications, including quantum cryptography. Since traditional cryptographic codes, such as RSA and ICE, can be cracked by quantum computers in a fraction of the time it takes for traditional computers, new cryptographic algorithms providing more privacy and more security are needed. Quantum computing, enabling advanced and fast algorithms in biology and chemistry, can significantly speed up the analysis of protein structures and the discovery of new drugs. This is anticipated to result in a plethora of breakthrough in diagnosis, treatments and cures in the health industry. Quantum computers will enable us to conduct more precise and detailed simulations of Earth's climate, thereby improving our understanding and mitigation of climate change. A wide range of optimization problems can be solved with quantum computing, from supply chain optimization to traffic control and even financial portfolio management. In addition, machine learning, material design, speech and image recognition, fault-tolerant quantum programming languages and systems, efficient communications, as well as factorizing big numbers are likely to benefit from breakthroughs in quantum computing. As a result, quantum computing can improve efficiency and decision-making in an impressive number and range of industries. Advantages and disadvantages of quantum computing. Quantum computers have the following advantages over classical computers. First, due to the principles of quantum mechanics, such as superposition and entanglement, quantum computers are able to perform calculations exponentially faster than classical computers. Second, quantum computers are capable of performing multiple calculations simultaneously, making them ideal for solving complex problems that would normally take classical computers years to resolve. Third, quantum computers are expected to be considerably more energy efficient than classical computers, which could have a significant positive impact on our environment. However, despite the numerous advantages, we still face a number of significant challenges. Due to their delicate nature, qubits are highly susceptible to errors and decoherence. For quantum computing to be reliable and scalable, robust error correction and fault-tolerant quantum computing techniques must be developed. The construction of quantum computers requires precise control and isolation of bits, which can be extremely challenging. Further advances are needed in the fields of materials science and engineering, as well as quantum hardware in order for it to be stable and scalable. Conclusion and future directions. Currently, quantum programming languages and algorithms are in their infancy. Software development will be crucial to harnessing the full potential of quantum computers. These systems are required to operate in complete isolation and in a cool environment to minimize interferences while standard computers operate at room temperatures. The widespread use of quantum computers in our daily life is expected to take some years. However, we must be prepared for this eventuality since our existing systems are extremely vulnerable to the effects of quantum computing. Essentially, quantum computing exploits the unique properties of quantum mechanics, such as superposition, entanglement, and quantum gates, to perform complex calculations that are impossible or impractical with classical computers. A key to unlocking the full potential of quantum computing is the development of efficient quantum algorithms and the resolution of challenges such as decoherence. It is possible to usher in a new era of computing with unprecedented speed and efficiency through quantum computing. Immediate challenges in quantum computing include widespread use of quantum computers with reasonable numbers of qubits, as well as realization, verification and testing of small quantum networks with efficient quantum crypto and communication systems, and demonstration of entanglement over long distances. In the near future, we can expect breakthroughs in areas such as quantum error correction, quantum distributed computing, quantum optimization, quantum learning theory, and new quantum algorithms. Other breakthroughs to look out for in the future include hybrid quantum classical systems that combine the strengths of quantum computers with classical computers may lead to more powerful and practical solutions. A quantum internet would provide ultra-secure communication and distributed quantum computing. Information sharing and processing could also be revolutionized by the development of a quantum internet. Quantum computing could potentially contribute to the development of the metaverse by enhancing computing capabilities, improving the efficiency of data processing, and enabling more complex simulations. Using quantum computing to advance artificial intelligence could lead to unprecedented advances in machine learning, data analysis, and many other fields. Keep up with the latest breakthroughs in information and communications technology. Subscribe today and stay ahead of the curve.